哎，起来，请问通知一下那个谁，什么庄家珍啊？那谁帮我通知一下那个什么庄家珍？OK，好，疫情已经回复，大家在这边好，谢谢。
老师，张家珍说他的那个账号有点问题，可能要等一下才可以进来。
哦哦，
对，
好，那我们先上课，看一下我们是不是在录影了。OK，let me see，how can I hold on？等一下哦，我回一下国际处。喂，志宏怎样？志宏比较少诶，没有印象，大概就7、8千块吧，我记得。没有啦，没有什么报价，我从来没有付过超过1万块。好，好了，OK，好，好，拜拜。等一下，我回一下国际处。啊，等一下，为什么不见了？等一下啊，第2章。等一下啊，等一下啊，等一下，嗯，为什么这个东西又不对啊？Chapter Two。OK，庄家珍进来了，我看一下，庄家珍是不是进来了？OK，到了。OK，Yeah，let's get started. And so I would like to share the screen. Going to read out the chapter 2 today. Hold on. Yeah, I know. Like to share this one. Okay. Can you see the PowerPoint slide?
哦，可以看得到。
Okay, sure. So last time, I think we get right here. Yes. Okay. Good question. Yeah, hold on. This is not the right way since you're allowed to type it. Hold on. Yeah, let me do that. Okay, let me do that. I want to share the screen. Hold on. Microsoft Office and hold on. Yeah, let me do that. The typing tab control chapter 2. Chapter 2. Okay. Okay. Yeah, it's kind of going on. Okay. I hope it's better. So last time we getting it right here. So the transfer function, hold on, how come? It's strange. No, not this one. This is defect. Hold on. Yeah, I don't know. Yeah, let me do. Good data. I hope this is getting right since okay, this is getting better. AR model. This is yeah, backwash operator. We have done. Well, this is backwash operator in transfer function. In terms of Q, and so in general, okay, then yeah, that will be the transfer function B over A. This is B over A. That's equal to transfer function. Transfer function. So let me address a little bit about the transfer function. Transfer function is highly relevant to the stability of the polynomial. So the polynomial A asterisk of Q, in terms of forward operator, is called the characteristic polynomial of the system. So the A asterisk of the Q forward operator, yeah, it's the key. So how can we determine it is key to the stability of system? So going to solve the characteristic equation. That's called the characteristic equation. To let n equal to 0 to solve the root. To solve the root. The root is Q. Hold on. The root is Q in A asterisk. Okay. And then the root in the root is the Q raised to the power -1 in A. So they are reciprocal. So if it is a 1, this is 2, the other going to be the 1 over 2. So they are reciprocal. Let me type it. Can you see my taxing? Can you?
可以看得到。
Okay, sure. So equivalently B over A is equal to H. So yeah, so also as a transfer function in Q minus 1. So in general, stable system is a system with a bounded response, that is finite variance. That is to say, the variance bounded. That is to say that is the variance is less than infinity. So this is a bounded condition, or called bounded variances. So having a finite variance, so it turns out that the roots of the characteristic polynomial determine the stability of system. That is a pole called a POLE, pole. Yeah, like a pole that we just raising the flag. When we was a student in the morning, we sing the national anthem, or just yeah, this is like a pole. So system is stable as long as the roots of the we call the quality characteristic, like this, A asterisk, characteristic A asterisk, this one, A asterisk equal to 0 reciprocal polynomial are all inside the unit circle. So this is let me see that. How can I type it? Absolute value. This is A control, AVS. The AVS of the Q is less than 1.0. Okay, absolute value. Within the unit circle on the complex plane. Complex plane. So on the contrary, alternatively, a system is stable if the roots is greater the root of A Q minus 1 equal to 0 are all strictly outside the unit circle. So this is ABS. Absolute value of the Q minus 1 actually is greater than 1.0. Okay. So still in the complex plane. No, should be this is typo. This is complex, PLANE. Okay, this is typo, PLANE, not PLAN. Complex plane. Okay. Typo. So then let me put an example. For example, the stability of a difference equation model, example 2.1. Please open the textbook. Yeah. Let me get your textbook ready. In the meantime, on page 51, please. On page 51, the yt equal to the phi, yt minus 1, so understandable. It is an autoregressive model. Of the first order. the first order. And yeah, I can see that xt minus y between y and yt minus 1 is autoregressive. Between the yt and xt minus 1, so it is referred to transfer function type. If it is yt and yt minus 1 is referred to autoregressive. Okay, see the differences? Yeah, it's quite straightforward, right? Is there any question so far? 哎，庄大这没问题。
目前应该没有。
那个呢，王力宏？
还没有。
Okay, sure. Then, we move the yt to the left-hand side to factor out yt. So this is 1 minus 5 back-Cauchy operator times yt equal to the right-hand side xt minus 1. So a polynomial on the left-hand side. A of the back-Cauchy operator equal to the 1 minus 5 back-Cauchy operator less than equal to 0. We solve the root. You solve the root q minus 1, right? So the q minus 1, solving the a back-Cauchy operator equal to 0, then the root is equal to the 1. Yeah, let me see. Back-Cauchy operator equal to 1 over 5. So that needs to be greater than a unit circle on the complex plane. So absolute value 1 over 5 got to be greater than 1. Yeah, equivalently, we say that the absolute value of 5 need to be less than the unit circle, less than 1.0. So that is to say 1 is less than, yeah, it's less than 5 and greater than 1 and less than plus 1. Am I right? Like this, right? Get it? Okay. And so this is called the characteristic equation. Characteristic equation. Oh, called a polynomial. I'm sorry, polynomial. And then move to the next one. Well, this is it's the most difficult part. This kind of confusing and tedious and confusing. So this is called the jury's test. Let me, yeah, see the page 52. See the textbook page 52, please. The jury test now sometimes it's very difficult to solve the root. Solving the root of higher order of the model. I'm sorry. Having a higher order is difficult. It's very difficult. This is the problem. Then in terms of that, there's a jury test for stability comes out. So given, first of all, need to put everything in the place in terms of the reciprocal polynomial. So that is A as the risk of the Q in terms of forward operator. Forward operator in terms of Q. Like this, like A asterisk in terms of Q, forward operator A0, Qn, A1, Q raised to the power n minus 1, Q2 n minus 2, and so on. So this is not L. This is should be this the dot dot dot, not L. So from the following table, we play the order. Let me do that. Okay. So you see that this is the order, right? This is not L. This is dot dot dot. Can you see my drawing? Can you? 看得到那个老师的那个紫色笔吗 ？Can you?
有看得到。
Okay, sure. And and place the order like the A0, A1, A2, and so on to place in the first row. Okay. The second row is right here. Just is placed in a reverse order. So like this, and then the last one become the second. The last two become to the second. The last three become the and so on, and the first one become the last one. So this is the reverse order. Yeah, let me see. Okay, hold on. Like this. This is an ordinary order, and for this and the reverse order, and the place in the second row, right? Okay, then I would like to compute the ratio. This ratio. So this alpha n, since if we have order n of order n, so the order going to be decreasing. Like this. So if this is the first ratio n, then second reduced by 1 alpha n minus 1 and alpha n minus 2, alpha n minus 3, and so on and so forth. So the order is decreasing until when we stop until the order is reduced to 1. Okay, then we stop. So in such a case, then the term saying some. Okay, let me do that again. Okay. Then this is the first iteration. Then based upon A0, and the AN and the alpha n, then the component can be computed, A0 and minus 1. So this is the order of the n. So this is the order of the n minus 1. So this is order of n minus 2 until this is order of A0. Then we stop. Until the last iteration, only one term remains. then terminate, and terminate. Then we stop. So how can we compute that? Then this is the ratio, and this is, so in order to calculate this, based upon this, based upon this, and based upon this, to compute the first component. In order to compute the second number, use this, use this, and this. Then we get A1. How can we get A2? A2, an minus 2, and alpha n, and so on and so forth. Then, so for each iteration down forward, so there's a one component less than, yeah, let me draw it. Oh, no, let me draw that. Let me draw that. Okay. Then, for this iteration, how many components we have? N, A0, A1, A2, AN minus 1, AN. No problem. For iteration 2, N minus 1, we have, yeah, this. I'm sorry. A0, A1, A2 until N minus 1. So this is a one turn reduction. So every time going to be a one turn shorter until blah, blah, blah. There's only one remain, then we stop. Get it? Zhirong, do you understand what I'm talking about, Zhirong?
Yeah.
Okay, cool. Cool. Then we move to the next one. So where? Please turn to the page. Page 52, textbook. Page 52 of the textbook. So where, yeah, this is a little bit confusing. So where the, let me do that. This one equal to this one minus this one. So how can you get that? This is alpha k. Alpha k is right here. Right here. Okay. Then this is aik. This is akik. This minus this. So this is this minus this times this. Then we get, I'm sorry, this I k minus I. I'm sorry. Yeah, it's a little bit confusing. Okay, hold on. This minus this times this to get this. Okay, according to the formula on page 52 in the middle. Okay, then if and only if all the A asterisk of the Q has all the root inside the unit circle, since this is a forward operator. Forward operator. Then, if only if has all the root inside the unit circle. If and only if 在中文叫做你们写一下叫弱且为弱。Would somebody would like to explain what is if and only if？ 弱且为弱，应该小白兔你说说看好了，弱且为弱是什么意思？ Hello，小白多。
我不会解释哎。
哦，那个志宏好了。
是逻辑运算是互斥的意思吗？
不是，那就换家珍好了。家珍can you help to explain？
只有当这个状况，
什么？你讲清楚点，老师听不见。
只有当这个状况。
哦，那力宏，你可以帮忙解释吗？力宏？
这个假设是唯一的一个假设。
OK， 应该这样。若你看啊 if and only if， 就是说我们讲若 P 则 Q 就是 if， 对不对？若 P 成立 ，Q 就成立，对不对？然后 if and only if 就等于是若 P 则 Q， 然后反过来若 Q 也则 P， 懂意思吗？就两边要同时成立，就等于这条件很严苛了，就等于是说我假若 if and only if 来看一下哦，来，老师用中文说一下，在这里比较麻烦一点，来看一下哈。若且为若就是说假设，来等一下，来看一下哦。假设什么意思？假设说我今天这个特征方程式所有的 root 都 inside the unit circle， 代表什么意思？来，利用。假如说我这个所有的根都 inside the unit circle， 代表什么意思？代表说我这个 equation 是什么 stable， 对不对？
有解啊。
OK， 假如说是稳定，那我最后一个 term 它就会大于等于零。这个 term 是什么？在这儿，这个 term 就是这个，对吧？我中间用 juris 这样一直降阶到最后一个 term， 对吧？是不是？降阶到最后一个 term。好，再来，就等于是说，好，那等一下跑哪去了 ？OK， 哎，跑哪去了？好，降阶到 term。那假如说我最后一个 term 等于0的话，代表说我这个方程式是它的根是在 unit circle 里面，所以说我只要所以若 P 则 Q， 假如它是稳定，它这个 term 就会大于0，假如这个 term 大于0，它就稳定，这就叫做若且为若，好吧 ？OK， then we have an example of the order 2. So that really explains how the juris test can be applied to the examination of the stability condition. So this is order 2. I'm sorry. Question is the regressive model of order 2. Okay, like a white tape, this is first order phi 1, second order phi 2. This is plus the arrow 10. Then we moved this and this to the left hand side. So originally we have a 1, then we multiply the q. So already in terms of backward operator, this is going to 1 minus phi 1, phi 1, and the q minus 1, and the minus phi 2 Q minus 2, right? Originally, this is so this is the A of the Q minus 1. Remember, right? You see that? Then, however, so this is the characteristic equation. Then we turn into the forward shoe operator. So this is the backward shoe operator. We turn the forward shoe operator and multiply Q squared. So into that, the Q1 multiply 1 times Q squared, and the Q squared times Q minus 1. This is a Q. And this is the Q squared times the Q minus 2. This is Q0. So that's a 1. So this is a polynomial. So this is a characteristic polynomial in terms of the backward shoe operator. Backward shoe operator. This is polynomial in terms of forward shoe operator. So I'd like to use this to put into the jury test. So this is a 1 and minus phi 1 minus phi 2, right? Then we move to the next one. So this is a 1 minus phi 1 minus phi 2. Where does it come from? Right here. 1 minus phi 1 minus phi 2. Okay. Then 1 minus phi 1 minus phi 2, then we put it in the reverse order in the second row. So minus phi 2 right here, minus phi 1, and the 1, this is the first position, and the place in the last position in the second row. And then since the k equal to 2, so this is the iteration, I'm sorry. So this is k equal to 2, so this is alpha 2, alpha 2. Alpha 2 is this. Minus phi 2 divided by 1, this is minus phi 2. This is the ratio. So what does this ratio come from? Right here. I'm sorry. I'd like to compute this ratio. And then, so this, in terms of this, in terms of this, and in terms of this, to compute this. Okay. So you're going to just calculate. You just so going to practice at home. In terms of that, use this to calculate that, and use this and this and this to get this. Okay. Okay. Then hold on. Now it is quite clear. This is iteration 2 and down to iteration 1, and down to iteration 0. Then we stop, right? If it start with 3 and 3, 2, 1, 0, then we stop. Okay. Would like to perform the next iteration, like this. Then this is the order. So the second become the first one. The first become the second. So we have a iteration corresponding to k minus 1. So then in terms of this, and we have alpha 1. How can we get alpha 1? This divided by this equal to the alpha 1. Yeah, that's kind of messy. I need to clear up a little bit. Okay, I'm sorry. And then how can we get alpha 1? This divided by this. Then we have k equal to 1 with use this number and this number and the ratio to generate this number. Okay, So every time reduced by 1, there's only 1 term remain. So we like to this number greater than 0 to be stable. To be stable. Yeah. Then the key for now is how we can determine this term is greater than 0. So what is the condition of the phi 1 and the phi 2? On phi 2, right? Okay. Is any question so far? 来，这有没有问题？没有啊。大白兔 ，Hello。
没有。
Okay, then. Okay, since condition for stability condition. Condition, the 1 minus phi 2 got to be greater than 0. Hold on. This got to be greater than 0. This got to be greater than 0. And then. Oh, I'm sorry. My mistake. Okay, then. My mistake. Okay, so that is to say, let me do it again. The condition, all the leading component need to be greater than 0. Not only the last one, A0, K is 3, 2, 1. So for K0, 1, 2 until the order n minus 1. 来，老师刚刚这边修正一下哦，它代表说每一次计算的 leading component 都要大于0。leading component 要大于0 ，leading component 要大于0，而不是只有最后一项，因为老师刚刚漏说了。等一下啊，漏说的意思是这里啊，这里，它是代表你看，它本来是假如是n 的话，它减1就是假如是4变成3阶层的那个 leading component 要等于0。2要等于0， 1要等于0， 0要等于0，所以说这个 leading component 就在这儿，这个 leading component 这里，这个本来是，假如是这边是2，这边变成1的 leading component 要大于0，这边1变成0的 leading component 要大于0。Okay, so then we understand the leading component is this need to be greater than 0 and this need to be greater than 0. So if this need to be greater than 0, how can we do that? That's easy, right? So 1 minus phi 2 squared need to be greater than 0. Yeah, that is to say phi absolute value of the phi 2 need to be between 1 and minus 1. That's it. Easy. So this, so got to be between 1 and minus 1. That's it. And then this need to be greater than 0. It's a little bit tricky. Then this need to be greater than 0. A little, so we just do the reparameterization. Let me see that. This is yeah, this one, and we factor out 1 minus phi 2. Yes, let me see that. 1 minus phi 2, 1 plus phi 1. Okay, then since this 1 minus phi 2 squared can be factorized into 1 plus phi 2 and 1 minus phi 2, right? So this is reparameterize this equal to the 1 minus phi 2 squared. Okay, then phi 2. And the minus 1 minus phi 1. This minus this. So we factor out. Yeah, let me see how can yeah, let me see. 1 minus phi 2. Yeah, so yeah, I understand. Since this is 1 minus phi 2 squared, right? So we have a 1 minus phi 2. This is a 1 minus phi 2, 1 plus phi 2. So we have this, and then we have denominator 1 minus phi 2. So we have a 1 minus phi 2 squared. No question, right? So this can be factorized in 1 plus phi 2. Hold on, let me type it. 1 minus phi 2 times 1 minus PHR. Hold on. Minus phi 2 and the 1 minus phi 2. Okay, then until now, I think there's just factor out the common terms. So this greater than 0, if this is greater than 0, so this, yeah, let me do that. If this need to be greater than 0, it could be the plus or minus, right? So since a phi 2 the phi 2 already between 1 and minus 1, so 1 plus phi 2 got to be greater than 0, no question. 1 minus phi 2 need to be greater than 0, so you just don't worry about this time. So this is a plus and need to be the plus. So this need to be the positive. So 1 minus phi 2 squared minus 1 phi 1 squared got to be greater than 0. So 1 minus phi 2 squared got to be greater than got to be greater than phi 1 squared is this one, right? So just 1 minus phi 2, 1 minus, so move to the left hand side. So this is 1 minus phi 2 minus phi 1 times 1 minus phi 2 plus phi 1 greater than 0. So it could be the plus or minus. So and then this is this or this. The both condition, either condition need to be satisfied. So under those conditions mentioned above, this got to be greater than less than 0, and this is less than 1. Phi 2 minus phi 1 less than 1. So finally, the geometry of the physical position. I'm sorry. Okay, look at the textbook. Look at the textbook on the page 54. Page 54. 54. Look at that. They're going to be a triangle. Right. Let me see. Is any? Hold on. I'm gonna stop. Okay. Let me see. How can we? Hold on. Hold on. Let me see that. Yeah. What time is it? I think we have a break. Okay. We have a 10 minutes break. After 10 minutes break, I'm going to show you the triangle. Okay. Thank you. Be sure to return after 10 minutes break. Thank you. 好，我们休息10分钟。为什么不行呢？Yeah, let me show. 好，先休息一下，谢谢。 Yeah, let me see that. Yeah, let me see that. to. All right. Back to class. Let me show you. Yeah, let me see that. What is that? Okay. Where am I? So that gotta be today. Statistics. No, share. I cannot. Right. Yeah, let me see that. Okay. See the page 52. Yeah, let me see that page 52. And like this. So see that in terms of that, this is implies the two condition need to be satisfied. Then they're going to be a triangle like this. Yeah, hold on, let me see that. No, I don't simplify matter only like that. Hold on. I don't know why can't I? Okay, so again, can be seen from the figure 2.7. Then the condition 2.2, 2.4 to define a triangle. This is a triangle. And on the plane, triangle region on the plane phi1 and phi2 plane, pairs of the value phi1 and phi2 inside the triangle of the figure guarantee stable dynamic behavior for the system. So, okay, they're going to be the homework for today. They're going to be due. Let me see. I'm gonna text it. Okay. The homework for today. So going to try to use the jury's test to compute the stability conditions of AR2 model. Okay, use the jury's test. And finally, you need to plot the feasible conditions. Okay, the homework for the day. For today, so it is due 2 weeks from today. You're gonna write it. Use an A4. Use a pencil. Try to show that, and draw the picture by yourself. Okay, then we move to chapter 3. 没有第3章的讲义吗？
老师我们没有。
OK, hold on. 我现在传给你们。Hold on. Yeah, let me do that. Yeah, let me do that. Time series. We're gonna pass it through the line. I think you can get it now. It is in the group. Get it?
有老师看到了。
All right, thank you. So we move to the chapter 3. So, well, I know this is spring break is coming. I know. Better not plan any vacation. No, I don't think you have the time for vacation. You need to devote yourself to my homework, the term project, and yeah, especially my student need to try perform some experiment on your thesis. And then so prepare reading the material and conducting experiment of the Professor Tsai's class and the Professor Tsai's homework, right? So yeah, you can just take a rest a little bit, but do not go far away from. So do not try 3 days or 4 days vacation, which is not possible. No. Okay, then we move to the chapter 3. I'll try to get them. All right, this time series analysis, chapter 3. In this chapter, we're going to address a model P, D, and Q. Q. So in here, Q is different from the forward operator. So chapter 3, ARIMA, time series models. The model was developed by Box and Jenkins, dated back to the 1970, and who both he and his school, his research school and research group, back in 1970 proposed a classification of stochastic difference equations called ARIMA. So AR stands for autoregressive. I stands for moving, and MA stands for moving average. So collectively, we call it also known as ARIMA model or Box-Jenkins model. They'll call the Box and Jenkins model. PDQP, the order of the autoregressive term, and P is the degree of differencing process. So we're going to difference why we need to difference the process. Why we need to difference the process data? Why? 立宏 difference the data. Difference 意思就是差分，我们为什么要做差分？谁知道啊？家珍知道吗？还是泽成知道吗？还是秦知道吗？
是要让资料变，
什么？让资料怎样
让资料非稳态变成稳态。
？Okay, cool. Yeah, correct answer. Try to make the data to try to produce stable data. Such as the not random. This is the random walk model. Also, difference the random walk model once then to make the random walk model to be stationary. Yeah, difference the random walk model wants the model's data to make it stationary. Yeah, that's cool. Then move to the mathematical representation. So ARP process model is given by the stochastic difference equation. Then YT equal to the psi, let's call this psi. Pronounce as psi. Pronounce as psi. So it is typically it's also known as an intercept. As intercept, which is constant but unknown. Yeah, so need to be estimated by the typically can use the linear or nonlinear least square estimation. So yeah, the process given by the stochastic difference equation, the phi 1, the first order times the y minus 1, phi 2, y minus 2, L is a dot, not L. And phi p, t minus p plus epsilon t, the epsilon t is the error term. Following a white noise sequence. White noise sequence that is an N01. This N0 and 1 with 0 center at 0 and with the univariance. I don't know. Why? How come? Very strange. So very This is a bizarre character cannot be recognized. Yeah, it's just a transfer. But I transfer into the PDF. Hold on. I transfer into that. Big data. Bigger. Chapter 3. No, I cannot do that. No, it is not possible since once I use a PDF, I cannot use any colorful painting the pen drawing, so I cannot. So I still need to use that. Yeah, okay. What should I do? Okay, keep using that. All right. However. That's strange. I don't know.这边可能因为我不知道为什么会出现这样的问题啊？我也不知道为什么会出现，为什么 PDF 就不会奇怪 ？Okay, however, then okay, just use it. However, you understand what I'm talking about. This is Y tail. Okay, this is Y tail. And YT tail, phi 1 T1 tail, and phi 2 T minus 2 tail, and dot dot dot. This is not L. But YP, this is a Y tail T minus B plus epsilon T. So move those to the left hand side. So we like to equate. So this is a polynomial YT tail equal to the epsilon T. So a polynomial times the YT tail. So the Y tail, YT tail equal to the YT minus mu. Mu is the process mean. So that is to say, whenever process is stable, then E has a fixed or called a constant or constant mean, right? Once it is stable, then for each one, so the YT tail so that is the YT tail is defined as the YT minus mu. Likewise, anything YT, if the YT tail t minus 2 is defined as a yt t minus 2 and the minus mu. Always deviation. This is the deviation from mean. Okay, we like to represent as a y something tail. So the y tail, so the epsilon divided by a right here. As long as a is stable, so it's always invertible. However, sometimes it is not necessary to be stable. So an ARP process is stationary if the A polynomial is stable. So stability condition. Based on the A polynomial of the back. As long as the stability condition is satisfied, the A need to be stable. If the A is stable, process stationary. If the process stationary, A is stable. So if the root is outside the unit circle, so we like to solve. So this is outside the unit circle. If this outside unit circle, this is the stable, polynomial stable, then process is stationary. So let me type it. Outside the unit circle, then, and the polynomial is stable, then if the polynomial is stable and the process is stationary. Okay, this is the logic. Outside the unit circle, polynomial is stable. If the polynomial is stable, process stationary. All right, and we put example. Pretend to the textbook, the section 3.1 on page 70. On page 70. See that the t tail equal to the phi 1 yt minus 1 tail plus the arrow. Then move to the turn to the left hand side. So 1 minus phi 1 backward operator yt tail equal to the right hand side only equal to the y noise sequence. So a polynomial is a backward operator equal to 0. This is a characteristic equation. To solve it for backward operator, the backward operator equal to 1 minus phi 2, since it need to be outside the unit circle for process to be stationary. So 1 over phi 1 needs to be greater than 1.0. Then absolute value of the phi 1 is less than 1.0 unit circle. Know that AP. Okay, so this is our stationary condition. Then, so know that the ARP, the P is the order of the autoregression model So autoregressive now is not always stationary. So under what condition are they stationary? It totally depends on A, polynomial, or the A asterisk, the forward operator. Either way. Then rationale. Please to turn to the page 71 in the middle. The stationarity condition. I'm sorry. Stationarity condition. So in the middle, appended 2C show the mathematical details, explaining why is it that the roots of the characteristic equation determine the stationarity of process. That explanation in the appendix is based on these transforms. So we can provide some further details or rationale for this important fact from a more intuitive point of view. So consider solving the AR1 process by repeated institution of the YT minus K tail in that recursive equation. So we will get that like this. We call it recursion, repeated recursion, repeated substitution. By doing that, repeated substitution, then this YT tail, this is a phi YT tail, and YT minus 1 tail is replaced by this. This is a phi. The YT minus 1 tail equal to phi times the YT minus 2 tail. Cross arrow. No question. Then move to so this is the arrow, no question. Y sequence of phi t minus 1. The phi epsilon t minus 1. And this is a phi square, so this is phi square. And t minus 2 is replaced by t minus 2 tail equal to the phi t minus 3 tail plus epsilon t minus 2. So this is, keep doing that. The phi t minus 3 tail plus the epsilon t minus 2. And then going further, factor out phi cubic t minus 3 and the cubic epsilon t minus 2 and the phi t minus 1 plus epsilon. So as long as the phi between 1 and 1, okay. Phi is less than plus 1. What is it? So what is going to happen? What's going to happen? Since this is 1, no question. And then the phi is between 1 and minus 1, so it must converge it. It must converge quickly. So this is phi squared, the phi cubic, then phi quadratic. Blah blah blah, and the phi fifth order, sixth order, seventh order. So it is exponentially decaying. In phi, exponential decaying since the phi between 1 and -1. Like 5.9 squared is 6 point. Yeah, let me see that. 0.81. 0.81. The cubic equal 0.72, and quadratic. I'm sorry. Quadratic is 6.5, and the fifth order 0.5, seven order and keep doing that. This is 0.4 or something. The exponentially decaying. So look at that. We just YT tail is this one equal to the summation phi j epsilon t minus j starting from 0 epsilon t. This is epsilon t minus j starting from 0 to infinity. So just keep substituting the repeated manner, then which can be represented into an infinite series. Number of a series involving phi, right? An infinite number of the series involving phi. So this is phi j, and factor out the minus j. This in terms of backward operator. The backward operator raised to the power minus j. Epsilon t. So look at that. This is like a Maclaurin series. The Maclaurin series. So it can be represented as a 1 minus phi. Since the starting j is 0, and so this is a 1, 1. If this is j is equal to 1, this is a phi, and backward operator minus 1, and phi squared, backward operator minus 2, and so on and so forth. So 1 minus phi backward operator. This is infinite. So how can we make it stable? Easy. Phi need to be between -1 and 1. -1 and +1. Got to be fall within this region. So this is an infinite series. Infinite series. Okay, then we'll move to the next page. For AR2, so then that is related to the page 71, equation 3.4. The textbook. Okay, I'll be back in a minute. I'll be back in 2 minutes. Don't go away. I'll be back in 2 minutes. Alrighty, look at the AR2 on page. Similarly. Okay, page 74. You need to read a book, please. Read the book. And read chapter 3 for sure. Okay, look at the example 3.2 on the top of the page 74. The example 3.2 AR2. YT tail equal phi 1 t minus 1 tail, phi 2 t minus 1 tail, and those two move to the right hand side. So A polynomial equal to 1 minus phi 1 backward operator, phi 2 backward operator. Hold on. This is something I missed. I'm sorry. Oh, I haven't gone to the estimation, so don't worry about that. Which can, if this is true, so A polynomial YT, A polynomial YT should be YT tail. No, it should be YT. This is typo, so this should be YT tail. YT tail. EILD, YT tail, YT tail. Equal to, by solving the equation A polynomial equal to 0, applying jury's criteria we just mentioned in the last class. The condition for an AR2 system to be stationary are like this, following. So what is the geometric region for this one? So like this is like going to be a triangle, right? A triangle like this, like this. So in here is a phi 1. So horizontal going to phi 2. So within that region, this is a feasible region inside the triangle, right? Okay, then. So move to the ARP. Section 3.1. This section 3.1.1. See the section 3.1.1. So mean value of stationary equation. So expected value is a mean value. Expected value is equal to the mean value. So so mean value of the stationary ARP as long as it is stationary. So so expected value, this is the psi, called the psi, SAI, pronounced as psi, is in the Greek letter. Quick ladder. Phi 1 t minus 1, phi 2 t minus 2, and L is dot phi p yt minus y minus p plus the arrow turn. Then collectively, which can be represented in a simpler form, the mu equal to the expected value of this one. So this is psi plus expected value of the, yeah, that's a little bit confusing. Yeah, look at that. So expected psi is equal to psi, no problem. Expected value phi 1, expected yt minus 1 is expected value of the yt minus 1 equal to the mu. Since process, let me say that, stationary process has a fixed mean. Since we prove, as long as the process stationary, you got to have a fixed mean. So expected value of the phi 2 yt minus 2 is a phi 2 mu, and blah 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 until the phi p mu. Then they can collectively to represent in a single form summation phi j mu. Then we move the second term to the left hand side and factor out mu. There's a mu 1 plus summation. No, this to this is a mu minus. So there's a minus right here. So minus summation of the phi j mu. So this is a 1 minus summation phi j, factor out mu, equal to the right hand side psi. So mu can be represented as the psi divided by 1 minus summation phi j. So, okay. So from this equation, what can you say? What can you say? 力宏，从这个方程式，你能不能下一个结论 ？What is the implication of this equation? 力宏 ，Can you?
No, not yet.
Not yet. 家珍 ，Can you? 志宏，
老师，我还没有想法。
那群，
老师目前没办法。
想没办法，到底有没有办法？来，那个小白兔，
我也无法。
哦，你也无法啊。好，休息10分钟，我们等一下再来讨论。OK。 All right, back to class. 来，我问一下大家好了，用中文问可能比较清楚。来问一下大家，就是来看一下，这 mu 就是它的自成平均数，对。psi 是什么 ？psi 是它的截距项，对不对？假若我都没有自我相关 phi j 等于0，对不对？是不是我的自成平均就等于截距项，对吧？是不是？这没有错吧？啊，假如我自我相关是正的，一个是0.2好了，那本来截距项是10，那1减掉0.2就是多少？0.8。所以说，假如说我有自我相关，它的平均数就会比原来的截距项要来的什么大，对吧？就是自成的平均数就会怎么样向上提升，对不对？本来是从1的话会变成1除上0.8，变成1.25嘛，对不对？好，那小白兔我问你，那我自成从1变成1.25啊，不问志荣好了，那对于我们管制图有什么影响？
对于管制图会有什么影响？
刚刚的逻辑你们有听懂吗？刚刚的逻辑，刚老师讲的逻辑。
有懂。
OK， 好，那你看哦，我本来一直认为，假设我一直认为没有自我相关，所以说它的平均数就是 mu 等于 psi 嘛，对不对？我就用截距项当做它平均数来建管制图，一定是平均数上管制界限，下管制界限，对不对？
对。
好，来，我先把它画一下，平均数在这里哦，然后上管制界限在这里，下管制界限在这里。那问题来了，我中间来看一下，这边问题来了，看一下，我自我相关一跑出来，我的自成平均就不是原来的什么红色，是变成原来的1.25倍，对吧？对不对？那我中间有一些点就会这样跑啊，有一些就会超出我的什么原来设定的上管之间，那是不是就很多所谓的假警报？
对。
false 对不对？那这些点明明是正常，但是我用旧的思维、旧的管制界限，我就认为这些是什么？这些是 out of control signal， 那基本上观念就错误，就出现很多什么假警报，叫做 false positive， 对不对？positive 在机器学习里面就是什么 false positive rate 会变得很高，对不对 ？The false positive rate increases. False positive rate in industrial engineering, that means this is this consumer, this is a producer's risk, or called a Taiwan error. All right. Producer risk increase or the Taiwan error increases. So this is impact if there's a autocorrelation is present, and however we are not aware of that, then going to commit more Taiwan error. 然后是这样的话，我们的刑误差是不是增加了，对吧？这样大家有听懂吗？
有。
德成还有于浅听得懂吗？
听得懂。
Okay, cool. 那玉琴呢？
听得懂。
Okay, cool. 好。Then, we talk about a little bit further. Autocovariance and autocorrelation. Yeah, let me see how that translates into Chinese or Mandarin. Yeah, let me think about. Let me have a while to think about that. Autocovariance. First one called autocovariance. In Chinese, maybe known as 自我共变数 or something like that, or autocorrelation, autocorrelation function. Known as ACF, autocorrelation function. Okay, in Chinese, may be known as the 自我相关函数 of an ARP. And the YT tell, so phi 1 YT tell, phi 2 YT minus 2 tell, dot, 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 YP YT minus B tell plus epsilon T. And this, we multiply YT minus K tell and take expectation that is called the gamma K, gamma. This is the gamma. This is gamma K. What is gamma? What the gamma is? Gamma is autocovariance. Autocovariance, gamma. So gamma K equal to the expected value of the YT tail and the YT minus tail. And so you might skeptical, hold on. The covariance is defined as covariance of the X, I'm sorry. This Y is defined as the expected value of X minus mu, mu X times Y minus mu Y. All right. So this is a definition. Covariance X and Y between two variables equal to the expected value X minus mu X times Y minus mu Y. How come? Why there's a no mu X and no mu Y？ 哎，老师问一下，这边既然是共变数啦，那为什么没有减掉它的这个 x， 就是它的这个平均数啊？没有减掉 x 期望值的 YT 跳，为什么？王力宏， 你知道我的问题？
我想不起来，你以前有讲过。
等一下，那不要字哈，于群，你知道老师在问什么？于群，
期望值等于0。
Yeah, why? Yeah, this yeah, clever， 聪明。为什么？来看一下哦。YT， 等一下哈。YT tail 减掉它本身的mu， 然后 YT TILD， 来看一下这里，刚秦讲的很好，为什么 YT tail 的期望值等于0 ，mu 等于0？来，大白兔，你说为什么？因为 YT tail TILD 定义是什么？来，大白兔说 YT 减掉什么？减掉 mu 嘛，是不是？是不是等于这样 ？YT tail 是不是定义成 YT 减掉 mu， 对吧？那两边期望值，然后求取 YT tail 的期望值，是不是 YT 的期望值减掉 mu 的等于是期望右边等于是期望值 YT 减掉期望值 mu， 对不对？期望值 YT 是等于什么 ？mu 嘛 ，mu 减 mu 是不是等于0？所以说 YT tail 的期望值是等于多少？0嘛。就是为什么这个地方没有 YT tail 减掉期望值 YT tail， 因为期望值 YT tail 是怎样？0嘛。好，那我再问大白兔一个问题，那为什么 YT 减 K，YT 减 K tail 也没有减掉它的期望值？来，大白兔。于谦，也等于0啊，因为怎么样？我不管时间在哪里，因为它是 stationary process，stationary process 它有个共通点是什么？它有固定的什么？固定的 process mean， 有固定的制程平均，对吧？我现在不管你是 T 减1、T 减2、T 减 K、T 减100万都一样，对吧？这样懂了吗？
懂了。
好，再来 back to here。安婷知道我在说什么？
知道。
那家珍呢？好来 then keep doing that. The YT tail, YT minus K tail equal to YT minus 1, T minus K tail tail. And phi 2, T minus 2, T minus K tail tail. Blah, blah, blah. Else, blah, blah, plus the expected P, YP, T minus P, T minus P, T minus K, Y tail tail. And the epsilon T, T minus K tail. Okay, then those equations can be rearranged into a single form. Rearrange into a single form, like that. Like that. Gamma K is gamma K. In here, this is right here, phi 1, and T minus 1, T minus K tail tail. The time delay between T minus 1 and T minus K is K minus 1. Like this. T minus K minus T minus 1. This is a system delay. Is blah blah No. Okay, t minus. Okay, hold on. T minus 1 minus t minus k is equal to blah, cancel out. This is k minus 1, which is called the system delay. This is or system lag. The system lag. Okay, right? So then this is phi 1, and expected value of this is the gamma k minus 1, and the phi 2, and expected value of the yt minus 2 tail, yt minus k tail. This is tail. This is gamma k minus 2, and blah blah blah. Last one, phi p, yt minus b tail and yt minus k tail. This is k minus p. Okay, last one. Why the last one? How come this term? What is this term turn out to be? 问一下郑安婷好了，小白兔，就是像老师黄色圈起来的，为什么等于0？
误差项。
期望值等于误差项很好，
误差项等于0，
很好，讲很好。那看 epsilon k， 这是 t minus k 嘛，所以说这边是 t minus k 减1 ，t minus k 减2 ，t minus k 减 p 到 epsilon t minus k 来看一下哦。唯一它可能让它不等于0的是什么？看一下哦，看一下。来，老师写一下哦。这边是 等一下哦。epsilon，let me see that. epsilon t 期望值，然后乘上 epsilon， 然后这边是 h t 减 k。来，小白兔看一下哦。Expected value of the epsilon t 减到 epsilon t 减 k， 因为 epsilon 它都是 error， 所以等于 epsilon t 减0乘上 epsilon t 减 k 减0，因为它的平均数都0，因为它是白色杂讯，所以这个东西代表期望值 expected value epsilon t 乘上 epsilon t 减 k。安婷，这代表什么意思？求它的什么共变数，对不对？就是 epsilon 在 t 跟时间 t 减 k 的共变数，但是我们知道它白色杂讯，它是 IID， 对 IID 这个东西代表在不同的时间点它是什么独立的，独立的共变数就等于多少？就会等于0，对吧？是不是？安婷？
对。
So this is IID. So this is independent and identically distributed. Since they are IIDs, and since they are IID, then the covariance is equal to 0. Okay, 这样懂了吗？ Okay. Okay, then we're going to wipe out the original mark to make it cleaner and to explain further. Okay. Then we have this, no problem. Then divide by gamma 0. Gamma 0 equals sigma y. 来看一下哦 ，zero 就代表 no time lag， 没有 time lag 就是原来的 sigma y 平方，它就不是什么自我相关共变数，跟自我相关没有关系，因为零是代表什么意思？我 yt 跟 yt 做什么共变？那 yt 跟 yt 做共变就是 y 的什么变异数，没有共变的问题，因为它的 time lag 等于多少？0。OK，divide by gamma zero on both side. Gamma k divide by gamma zero equal to the phi 1 gamma k minus 1 divided by gamma 0. This is the rho k minus 1. Rho is ACF, the autocorrelation function. Correlation function. 我们本来有个自我共变，自我共变除上自乘变异数就变成自我相关函数。So gamma k divided by gamma 0 is a rho k. Rho rho is the ACF of time lag k. ACF rho k. This is rho k. I show rho k. Rho k. This is k. So rho k equal to gamma k divided by gamma 0 equal phi 1 rho, the rho k minus 1, and the phi 2, the gamma k minus 2 divided by gamma 0, this is the rho k minus 2, L is dot dot dot, and the phi p gamma k minus p divided by gamma 0, this is the rho k minus p, right? So this, the rho k equal to phi 1 rho k minus 1, phi 2 k minus 2, blah, 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 and the phi p k minus p. Right. So this is a recursive question. Okay, then going further. Now we move to page variance. Okay, page 75 in the textbook. Please refer to page 75. To page 75 in the textbook. Okay, so variance of the NARP from equation 1 yeah, this is equation 1. This is equation 1. From here, equation 1, let k equal to 0. Let this k equal to 0, rho, the gamma 0 equal phi 1, and so on and so forth. Okay, then. No, let k, I'm sorry. This is k equal to 0, gamma k. Hold on, let me see that one. Okay, like this. This is the blah, 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 epsilon. Okay, rho k. So if the k equal to 0, gamma 0, since k equal to 0, we don't have, this is 0. Yeah, let me see. Okay, then since gamma 0 equal to the sigma y squared, so when there's a no time lag, then gamma 0 going to be equal to the process variance. No question about that. So gamma 0 equal phi 1, k equal to 0. 0 minus 1 is a minus 1, so gamma minus 1. Gamma, excuse me, minus 1 equal to the gamma 1. Why? 来，我问一下泽成好了，为什么 gamma 负1会等于 gamma 1？ Yeah, question 快点啊！
来想不太到。
来看一下哈 ，gamma 1是什么意思 ？gamma 就是自我共变嘛，就时间 t 跟时间 t 加1，对吧？时间 t 到时间 t 加1的什么共变数，对吧？那 gamma 负1是什么？时间 t 倒退到时间 t 减1，对吧？那中间的 system delay 是多少？一样啊，不论是向前1或向后1都是1嘛，对吧？
对。
所以说，不论是向前1或向后1，它的共变数应该要一样，对不对？它这个叫 even function。even 是什么意思？偶叫做偶，对不起，即偶函数，对吧？偶函数是吧？偶函数 ，OK。啊，这样可以吗？
可以。
Okay, this is gamma 1, phi 1 gamma 1, phi 2 gamma 2, and blah blah blah. Phi p gamma p, phi p gamma p, no question. Plus, yeah, there's a lot of things, blah blah blah. Wow, the whole thing. This is a y epsilon t yt tail. Yt tail replaced by phi 1 t minus 1 tail, phi 2 t minus 1 tail, blah blah blah, yp t minus p tail. Well, the only thing is epsilon t times epsilon t. 来，安停，期望值的 epsilon t 乘上 epsilon t 等于多少？安停啊。
0。
为什么会来猪头了？你就是猪头了，你又给我讲0。来，我是 epsilon t 乘上 epsilon t。来，为什么等于0？就是期望值的，把 epsilon 当做什么变数好了 ，x 平方好了。这样子 x 平方会等于0吗？来，我把它写一下，等一下。我写在旁边。Okay, be cautious. Be cautious. Look at that. This is epsilon t times epsilon t. Right? So this is expected value of the epsilon t minus 0 square. Right? 为什么减0？老师故意的啦。0刚好是 epsilon t 的什么？的什么均值？随机变数减均值的平方就等于什么？什么？它的什么？
变异数。
变异数。所以这个地方就 sigma epsilon 平方，这是这样来的，懂吗？安婷。
懂。
OK, then. Okay, then. 擦掉。Okay, then we have, so this is a gamma 0 finally turned out to be this term. This is blah, blah, blah. So, yeah, 稍待一下哦 Hold on. Okay, then back to class. I'm sorry. Gamma 0 equal to the gamma 0 is sigma y squared, no question. So we rearrange the form. This gamma 0. So let me see them. Oh. So we reparameterize this. We factor out by, yeah, let me see that. Okay, then divide by gamma 0. Yeah, let me see that. Okay, divide by gamma 0 on both sides. So gamma 0 divided by gamma 0 is equal to 1. This equal to 1. And phi 1, gamma 1, gamma 0 is a phi 1, rho 1, phi 2, rho 2, blah, blah, phi p, rho p is this one. Now plus epsilon, sigma epsilon squared divided by gamma 0. The gamma 0 is the sigma y squared. So we rearrange the form. So sigma y squared equal to the sigma epsilon squared divided by 1 minus summation rho j, phi j, and the rho j. Okay, so finally we arrive this. We arrive this. Okay, what is the implication from this equation? 来，家珍，从这个方式你又得到什么启示？家珍，前面这边有没有问题？来看一下，老师再讲一下啊。这个 rho the gamma 0就除 gamma 0就变1嘛，在这里对不对？然后这边 phi 1 gamma 1除上 gamma 0就等于 rho 1，所以这边是 phi 1 rho 1 phi 2 rho 2 phi p rho p， 然后这 sigma y 平方除上 gamma 0 gamma 0就等于 sigma y 平方，那 sigma y 平方重新整理以后就变这样。好，请问从这个方程式你有什么启示？贾扎，好，来那个利用。
他们说，如果那个没有自我共变的时候，这两个变数会这两个期望值会一样。
很好，他讲，哎，这个地方大家看一下哦，这个力宏讲对了哦，看一下，这边没有自我共变，这一个 term 就不见了，对不对？所以说我的 process， 我的制成的变异数就等于是什么的变异数？随机变相的变异数。但是我假如这个地方正相关，1减掉 0.2 变 0.8， 所以说我的变异数会什么？变大。 我只要自我相关，我的变异数就会从原来的 sigma epsilon 的平方变成 sigma epsilon 的平方除上这个分母，这分母是一个什么？小于1的正常数。所以说我的变异数就会比原来的 sigma epsilon 平方要来的什么大？这叫做 variance inflation， 叫做变异数的什么？变异数扩增。所以说我原来没有自我相关的时候，我的自成变异小；有自我相关的时候，自成就变异就变什么？变大了。这样清楚吗？听清楚吗？听。
可以。
来，于晴听得懂吗？
听得懂。
Okay, sure. So that's the reason why we always like to take the autocorrelation into account. Why? Since it happened all the time in practice. 为什么？因为它在半导体业，在现在的制造程序就是会出现自我相关，而且大部分都是什么？正的作用。Always. No, not always. Frequently. No, I would not say frequently. Often, positive autocorrelation is present in ordinary practice. This is the problem. This is the problem. Okay, then we have a conclusion like that. This is very important. So that is, can be referred to the page 75, on the bottom of the page 75. Okay, I'll stop here. I hope you enjoyed the class today, and there's a homework. You're going to show the stability condition of the A polynomial in the AR2 process. You need to be submitted in 2 weeks. And also you need to prepare your term project number 1. So you're going to bring your computer, bring your laptop to present your program in class. 就2个礼拜以后，每个同学要教的有2样东西。第一样东西就是今天的回家作业，就是 AR2 的制程的它的稳定条件。就 stationary 它的这个稳定的条件，你要用 A4 只用铅笔证明一次，用 jury's test 来去推导，到最后推导完毕之后，然后要再画出它的示意图，答案就是那个三角形。哦，这第一点，这2个礼拜。那2个礼拜以后要带自己的笔记型电脑去 demo 你的这个 term project 1的程式。好，在课堂上带过来，这样有问题吗？
没有问题。
Okay, then that will call it. So I would like to call it a day. So hope you enjoy your spring break. Is there any question you can send your email, or send a link message. No, like message to me. Also, I see you in 2 weeks. And happy spring break. Bye bye.
拜拜，谢老师。
拜拜。
谢老师。
可以 stop here. 我来 to 要怎么停啊 ？OK， 停止录音。